Okay, this is going to be a little discussion about a new energy transferring molecule. It's called NAD. Now, NAD has two forms, so I'm going to write it as NAD plus and NADH. And first, we're going to draw a picture of this NADH and this NADP. But before we do that, actually, we'll do something else. We're going to just briefly talk about what we call redox, or redox reaction. Because when you study this, sometimes you get the numbers and you do all the calculations, but you forget about what's actually happening. And so, very simply put, in certain reactions, redox reactions are all about electron transfers. Electron transfers. Okay? And so obviously if there's an electron transfer, there's somebody who's going to lose electrons. Let's make that lose electrons. And there's somebody that's going to gain the electrons in the transfer. The person who loses the electrons, we say, has become oxidized. The word is because oxygen was one of the first sort of oxidizing agents that we discovered. And so this term came from the element oxygen. It doesn't have to be oxygen. It's just commonly oxygen. But we use the word anyway. So if you lose your electrons, you are oxidized. And if you gain electrons, you are called reduced. Now, when you have reactions involving ions, it's quite easy to see who's gained and who's lost. If you lose electrons, you will become more positive, right? Because you lost negative charge. And if you gain electrons, you will become more negative. So an ion that shows up as a negative in a reactant, or an atom, I guess, that's involved in a negative ion, is going to clearly be the one that gains or loses. The trickier part, and this happens a lot in biological molecules, is when it's not a definite loss or gain, it's more like a little closer or a little further away. And so I'll use the example of this molecule here, this propane molecule. And we'll react this propane molecule with an O2 molecule. And we'll get products. We'll get carbon dioxide. Oops, so fix that. Carbon dioxide. And of course, water, right? HOH, something like that. And if we look at these pictures, we can see what's going on inside the atoms. So if we look over here at these carbon atoms inside the propane molecule, because they're hanging out with hydrogen, carbon is the most electronegative. It's the one that's hogging the electrons the most. And so all of these electrons that are in these bonds are sort of being pulled closer to carbon, because carbon sort of wins the electronegativity battle with hydrogen. In between the carbons, there's not much pull, because the carbon would pull equally on another carbon. But the hydrogens get pulled in, which means that inside here, these carbons, because the electrons are closer, we can think of them as being a little bit more negative, right, in this particular situation. If we look at the oxygen atoms, this is pretty much an even situation, so we wouldn't see any change there. Oxygen is going to pull on oxygen the same, so it's kind of like an even battle. And then we look over here and we see the other side. This carbon, he's changed partners. He's no longer with hydrogen. He's now with oxygen, who happens to be even more electronegative than he is, which means that now the electrons are being pulled outwards closer to the oxygen in that bond. That means that carbon is sort of like now a little bit more positive because his electrons are pulled a little further away. So what we can say is that in this case, what happens is because the electrons have moved farther away from carbon, we say that carbon is oxidized. So it's like a loss. He's oxidized, and we could say because the electrons are farther away from carbon in the product, farther away from carbon in the product, right, the CO2, than they were, or than in the reactant, which we would call, in this case, the propane, the C3H8. Now, of course, if you look at the oxygen molecule, if you go back to here, the oxygen molecule was in an even-steven share, competing with itself. But then, when it goes over here and it competes with carbon, it wins a little bit. So it has actually pulled electrons a little closer to itself, right? Because it's no longer fighting with oxygen. It's going to win the electronegativity battle a little bit more. And so oxygen will have its electrons actually closer to it in the products rather than in the reactants, which means that oxygen has been reduced. Okay? And that's what we mean when we talk about the movement of electrons in bonds. We have to look, and of course you can apply numbers, oxidation numbers, and you can do a tally and calculate and determine exactly who gets oxidized and reduced. We'll leave that for chemistry class. We just want to understand that if electrons move further away, that's the same sort of as losing them, and that is the same as being oxidized. Okay? And so now we can understand our new friend, because our new friend is going to be this big molecule that we're going to draw. Let's go down. Let's draw him. Okay? So we said his name was NAD, but we should write his full name. And he comes in two forms. He comes in an oxidized form and a reduced form. Okay? And so his full name is, I'm going to get a smaller font here, or a smaller line, is nicotinamide. Okay? He actually has nicotine in him, which is interesting. Nicotinamide, and an adenine, because he has an adenine as well. And he's a dinucleotide. Remember what a nucleotide is? It's a phosphate, a sugar, a ribose sugar, and a nitrogenous base. So a dinucleotide would have two nucleotides stuck together, and that's what NAD is. And he's quite large. So to draw him, we're going to have to jump down here. Got his name down? Nicotinamide adenine dinucleotide, NAD. All right. So the picture is huge. I'll show it to you here. So you have to leave a lot of room. If you only have like a quarter of a page left, you're going to have to either write small or move over to the next page, because it's going to take up a lot of space. Okay. So we'll go in black, and we'll try to write this as thin as possible. Over here, we're going to have phosphates. So I'm going to put two phosphate. Well, I'm going to put one here for now. And then I'm going to attach that phosphate to a carbon. And I'm not going to write the carbon. Remember that a bend in a line is a carbon, right? So there's a carbon atom there. And I'm also not writing all the H's, because we just know that the H's are just there as well. So here's the ribose sugar with its oxygen at the top. And then right here, we go up to a nitrogen. And then we have to, I'm going to sneak up just a bit. Then we have to make a little box, a little hexagon. I need a little space right at the very top, so I'm still leaving that space open, because that's kind of the action spot. Now there's some bonds in here. Okay, I'm going to draw him this way first. There's a carbon right there, NH2, and then a double bond O at this spot. That's the first dinucleotide. That's the nicotinamide part. Now we need to do the adenine part. Okay, so I'll pause for a second. Nope, I forgot one thing, very important. Right here, there's OHs, because this is a ribose sugar, right? So we can't forget those OHs. Okay, we'll pause for a second, catch up. Okay, a couple of things we have to sort of add to here. In this particular state that I'm drawing, there's a plus on this nitrogen right here. And even though I'm not drawing all the hydrogens in all the other spots, I'm going to draw one right here at the top. And we're gonna, that's the action site of this molecule. That's what's going to change after. And then we'll come back to that after and fix that up. Okay, so now we're going to go back to that phosphate and finish him off. But the reason I didn't draw that O in is because we have to kind of go down a bit. So I'm going to draw this to be sort of a long bond to give us some space. Maybe about that much. And then I can draw, oh, I should put the O in there though, eh? Let me just put a little space, maybe right about there. And let's put in the O. There's the other O for the phosphate. And this is linked to another phosphate. There would also be, I guess we should just be very precise, there would also be a slight negative on that oxygen right at the top. So we'll do that too before I forget. And then we'll go back to drawing this thing here, another phosphate, attached to an O, and an O down here, which before I forget, will also have a little negative sort of charge. Actually, we should put that, being precise, put the little negative near the top of the O like that. Okay. And then this is the O, good. And so then this O is attached to another ribose sugar. Which has OHs on the bottom there. And this one is attached to another nucleotide base. But the nucleotide in this case is one we're familiar with. And double bond on this side, double bond in the middle. Doesn't look like a very good double bond, does it? And then the hexagonal shape, with an N over here, and an N down on the bottom. And we got our double bonds there like this, and an NH2 stuck up here on the top. And that's pretty much it. That's adenine. Remember adenine? So you can see the top half is the nicotinamide part. It's one nucleotide. And the bottom half is the adenine part. Nicotine and adenine. And they're put together. So it's a dinucleotide. There's a phosphate, a sugar, and a base on each one. It's a dinucleotide, and it's called nicotinamide adenine dinucleotide. Okay. I'm going to let you draw that, and then we'll talk about the red part at the top, the action spot. So this is NAD, and if we go back up a little bit, at the top of the molecule, I'll put a big circle around it in green right here. This is the part of the molecule that is the action, where all the action happens. The ring with the nitrogen can actually accept electrons. It can grab two more electrons in the form of a new bond. Okay? So here's what happens. I'm just going to draw this section again. There's no point drawing the whole thing again. So what I'll do is I'll put a big blue line down here to separate. And over here I'm going to squeeze. Unfortunately, the board is not as big as I'd like it to be. So what I'm going to draw here is the same thing, a ring, a hexagonal ring with the nitrogen at the bottom. Double bond here. Actually, no, don't put the double bonds in. Sorry, my mistake. Take that double bond out. Because if you add electrons and you change the bonds, the double bonding part of this ring is going to change. Then we go over here and down here. We'll put our double bond oxygen where it was, and we'll put our NH2 over here. Down here, we're just going to put a little arrow, and we'll put to the rest. Because the rest of it doesn't really involve, or isn't involved in this redox reaction, so we don't need to draw it all again. Okay, so here's what happens. Instead of one H, a second H is added to this carbon. Okay, look at the first one, the one on the left. Count the bonds at that corner. There are 4. Carbon holds 4 times. But one of them is a double bond to another carbon. Right? If you then change the format of that, if you get rid of one of those double bonds, so what happens with the double bonds is instead they occur here and here in this molecule. So now those carbons are all holding on 4 times. Okay. Then what happens is this extra H is added at this spot, and the N is no longer plus, because the N has sort of gathered electrons closer to it. All right? It's gathered electrons closer to it because of the way the bonds have changed in the ring, and therefore it's no longer positive. It's now back to where it was. And the top of the molecule has changed. The carbon there has sort of attached itself to another H, which means that it's changed its position and bond as well. So this is what we call the reduced form over here. Reduced form. And he's called NADH because of the addition of an additional hydrogen molecule, or on top of a hydrogen atom. Just one sec, guys. And the other side, we would call it the oxidized form. So maybe over here, underneath this, we can write oxidized form. Okay? We'll back up. And we'll pause. So we can summarize this whole reaction of what's going on here in a little reaction. What NADH can do is it can lose 2 electrons, become oxidized in the NAD plus form, and then of course that H would be left over. Now that H could go into solution, it could be attached to another molecule, whatever happens there is the H, and in fact I think it would be an H plus would be left over. Oops. An H plus. And then we could also write 2 electrons, or sorry, 1 electron. I'm thinking about 2 because of the process later on. Plus an electron. But this process can also go backwards, right? It can also go backwards. So when it goes forwards to the right, it's being oxidized. And when it goes the other way, it's being reduced. And what we're going to find out is that what happens is these electrons are transferred to other molecules in a biochemical sort of chain or pathway. And by doing that, it changes the energy state of those molecules. And that gives them the kick they might need to change into something else and continue the pathway. Or vice versa. We might sort of create NADHs to be used elsewhere because maybe we need them in another part of a process. So that's sort of a shortcut to this. And that's the story of NAD. So we'll stop this one. We'll look at the next part in a separate video.